Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about stability. This is a topic that ties into our discussion of equilibria. Stability basically is a further condition on equilibrium, usually with static equilibrium. There is of course also a dynamic equilibrium, but stability is a little bit harder to define with that one. Unless you're near like a saddle point or something of the sort. So what is stability? Well, you know that a system in equilibrium has two conditions. So let's recall what those conditions are. The conditions for equilibrium are that the sum of forces on your object or system must be zero, and that the sum of torques on your object or system must be zero. So these are the translational and rotational conditions for equilibrium. If these two conditions are met, then the system is in equilibrium. If your system is at rest, then this equilibrium is static in nature. With that said, not all equilibria and not even all static equilibria are created equally. Consider, for example, I have here a book. This may not be the best thing to use for this, but I've got a book here. And it is at equilibrium right now. And, I can wiggle my hands quite a bit and it stays basically at equilibrium. As soon as I stop moving my hands about, it comes back to rest where it was before. Now, what would happen if I stood the book up on end like this? Well, it's still at equilibrium, but it's a little bit more wobbly, like I have to kind of balance it. And if I had a stable hand or a desk or something, I could in principle put the book on the desk like so and have it stay in equilibrium on the desk like so. But if I so much as wobble a little bit towards it, if I give it a little bit of a nudge, it falls over pretty quickly. And now that it's on its side like this, I can nudge it all I want. I can push it back and forth pretty good, and it stays where it's at. In principle, you could do something with something like this stylus pen, right? I can have it resting here like this, and when it's right here, it's at equilibrium. If I nudge it, it actually rolls back to this location a little bit because of the way that it's balanced. And I can also, in principle, stand it on the end, although this one has sort of a rounded end, so it's very difficult to actually do that. I can get it to stand on end, but the slightest jostling, it falls over. So in both cases, whether this stylus is on its side or whether it's upright, if it's stationary like that, if it's not actively falling over, it is in equilibrium. But it should be obvious to all of you watching this that those two equilibrium are not really the same. In one case, it's in equilibrium and jostling it kind of makes it return to that equilibrium point. In the other case, it takes a lot of, or maybe at least a bit more of effort, and any amount of jostling is going to make it fall, basically go away from that equilibrium. So this introduces to us a new concept in equilibrium called stability. So stability is, in some sense, describes whether or not the equilibrium is one that an object or system tends to return to when perturbed or tends to move away from when perturbed. So there are, broadly speaking, three types of stability or levels of stability. There's stable, there's unstable, and there's neutral. So stable equilibrium is something like you have a stylus like this pen that has an unbalancing feature. There's the little buttons on the side that kind of unbalance it a little bit. And that unbalancing feature is located at its sort of stable point. So put differently, maybe I happen to have an object that's shaped like a triangle, and I have it balanced like this on the ground. So this is a stable equilibrium, relatively speaking, because if I perturb this object slightly, it's going to tend to rock back onto its base. So in other words, if I were to perturb it like this a little, then it's going to tend to want to go back to its original position of just being on the ground again. Now, an unstable equilibrium for that same triangle would be more like balancing it about one tip. So it could be balanced like this, but any slight breeze, if it's perturbed a little bit from this balanced location like so, maybe we bend it ever so slightly this way, then it's going to tend to fall. Neutral equilibrium, I can't really do with this triangle. I'd have to actually kind of change the geometry of my system. But what if I have a ground like this, and instead of a triangle, I have a nice circle? So the circle's at rest somewhere, and if I rotate the circle, make it roll a little bit, so that instead of being at its original location, it's now here. If it's a perfect, I say circle, it could be a sphere or a cylinder in 3 dimensions. But if I move it from here to here, it stays at its new location. It doesn't fall away from it. It doesn't move back towards the original equilibrium. So that's basically like how the system behaves. So stable means returns to its equilibrium. So it returns to equilibrium if it is stable. If it's unstable, it falls or whatever, kind of moves away from the equilibrium and really moves to a new equilibrium. Any system that is falling away from an equilibrium usually has a second equilibrium somewhere that it's falling towards. And neutral means it doesn't really matter whether you place it here or there or this side or that side or whatever. It just tends to stay at however it's been placed. And if it gets moved, it gets moved and it stays in the new location. So what determines whether a system is going to be stable or not? Well, there's several ways to go about answering that. One is you could look at what the torques are going to tend to do to the system. So let's say that I have something like this, where it's kind of long and thin, but it is able to balance on one end like so. So here's my object, it's balanced on its end. When will it return to this position? Well, let's consider the center of mass for this. Right now, the center of mass is here, and so this right here would be my force of gravity. And therefore, there's no net torque about any of these things' axes, because this is the center of mass torque is essentially it's zero about the center of mass, it's zero about this axis, it's zero about this axis. It's maybe non-zero about some axes that it's not likely to rotate about because of the normal force, which is supplying a second torque about those axes. But the point being that this thing currently is at equilibrium. Now, if I were to allow it to move a little bit like this, so right now I'm just looking at it end on, but I guess I could draw it as a three-dimensional object in perspective again. Here's again that center of mass. And if I draw a dashed line downward, that center of mass is no longer over the base. That means that I'm going to have a net torque away from this base position. And so this is a relatively unstable. My center of mass is not over my original base of support. and so this thing will tend to fall. If, on the other hand, I rotate it only a little bit, so instead of rotating it at this angle here, maybe I rotate it only to, say, this angle here, then when I look at where my center of mass is in this case, if I draw a line down to vertical, it's still basically over the base, and therefore when I apply a torque about this, it'll tend to rotate back to being on the ground on that base. Okay, so one way of looking at stability is ask what direction does the torque make the thing want to move in. Now there's another way of looking at it, which is to ask, what is energy doing? What is energy doing? So it's a relatively stable equilibrium if torques tend to make the thing move back to the equilibrium point. It's unstable if torques make it move away from the equilibrium point. From energy perspective, let's look again at this pin or tower or whatever. So let's say that I have a very long, very thin object that I can balance at a point like this. All right, center of mass is right here, ground is here, so we would have a potential energy of mgh, where this right here is my height to, let's say, the center of mass of the object. And if, on the other hand, the object is lying on its side, so the ground is like this, and now I have the object doing this kind of thing, we can ask which of these has a greater potential energy. Whoops. The little drawing thing wants to make this a straight line, and I don't need it to be a straight line. Well, this right here is now my height, and so now I have u is equal to mgh. This would be erect, and this would be maybe like lying flat or something like that. So obviously the erect energy, UE, is greater than the flat energy. So one way of looking at stability is to ask, what is potential energy for that system? And the key is that stable systems tend to have minimal potential energy. Unstable systems have maximal local potential energy, and neutral systems, basically the potential energy doesn't change. So if I wanted to draw the neutral system here, whoops, let's draw a nice flat ground again. If I have an object here like this, and I have the same object over here like this, there's no difference in potential energy between these two objects. U1 equals U2. So how do I mean by local potential energy is at a maximum? Well, if I'm just allowed to pivot about this ground, I'm not allowed to leave contact with the ground, so this point is somehow touching the ground, then this right here is basically your maximum potential energy configuration. If I rotate this system very slightly to the left or right, the center of mass will be slightly lower than what it is here. And then over here, if I rotate this object about either corner or side or edge or whatever, rotating about this edge will tend to make this center of mass lift up like this. Rotating about this edge will tend to make the center of mass lift up like this. And either way, I've raised the center of mass and therefore the energy by rotating away from equilibrium. So that's stability for you. Thanks for watching.